All right. Thank you and welcome everyone to our Institute for Quantum Studies seminar this week. We're very happy to have our own Matt Leifer give the talk today. He'll be talking about contextuality and quantum interference. I just want to give you a brief history of his career. He started with a Bachelor's of Science at the University of Manchester, then did a Master's at Cambridge University, followed by a PhD at the University of Bristol, focusing on quantum information theory. He then spent time at the University of Waterloo and the Perimeter Institute, and he's been on the faculty here for a number of years. He's our program director in physics. Matt, the floor is yours.
Thank you very much. So what I want to talk about today is a little bit of a follow-on from things that I've talked about here before, in particular at the interaction-free measurements workshop last year. So I always end up presenting one side of the argument, and then at the end I have to like rush through some of the more interesting stuff, some of the stuff that's more interesting to me. So in this talk, I'm trying to focus on sort of the positive results that we have about quantum interference. And this is the first time I've put this together in a talk, so apologies if I make mistakes, and please do stop and ask questions if something isn't all that clear. All right, so let's try again. Okay, all right, so first of all, these are my collaborators on most of this work. It's obviously led by me and Rob Spekkens, and these three are now, the other three are now all postdocs. Giovanni and David were both PhD students when this started. Right, so basically there's going to be two main topics, and well, it's actually three topics. So these two topics here were done in collaboration with that group. This is newer work that I haven't published yet, and at the moment I've been doing it solo, but there are other people who might get involved. Okay, so the question that we really want to ask is sort of what's classical or non-classical about quantum interference effects? And so we have to ask, what does it mean to be classical as a whole? By the way, our president has decreed that section numbers on Chapman slides have to be Fibonacci numbers. And the official Chapman slides only go up to section 8. I had to make my own section 13 slide.
Innovative.
Yeah, anyway, so, but that's official Chapman policy now. Okay, so let's first of all talk, I mean, some of you see the Fibonacci numbers appear here in the Chapman logo. Let's start by asking when is something classical, and this is the kind of debate that comes up in the literature a lot. Okay, so you can produce a lot of papers by taking a phenomenon, for example, you know, just to pick something completely randomly anomalous weak values, right? and people can write papers saying it's classical, and other people write papers saying no, it's quantum, no, it's classical. Right? So you can generate a lot of literature, and that's not the only example by doing this. And one of the reasons why you can generate a lot of literature is because the questions has two ambiguities in it. Okay, first ambiguity is, what do you mean by classical? What assumptions do you make about classical models? Now, depending on the number of assumptions you make, you can prove that everything is non-classical, or you can prove that everything is classical. So let me give you the extreme cases, right? So you might say that something is only classical if it obeys the laws precisely, well, approximately obeys the laws of Newtonian physics and classical electromagnetism. And we also know that the Rutherford model of the atom is the correct kind of model. And so according to that theory, everything collapses into a pile of radiation, no matter isn't stable. So the fact that there's anything at all, like even the fact that there's a table in this room or that you exist, is genuinely quantum. Okay, so that's making a lot of assumptions about classical models. We can go to the other side. So some people say that, you know, quantum theory requires a revision of probability theory, but there are interpretations of quantum theory that don't. So if I say a classical model means something describable using classical probability theory, then I can look at something like de Broglie theory and say, well, that employs ordinary classical probability theory. And so everything is classical, right? So obviously, there's a spectrum of the more or less interesting distinctions that you can make between those two, right? So I'll be looking at one particular distinction, but to be fair, like some of the debates that happen in the literature have more to do with, you know, what's this definition? Do I mean classical wave physics? Do I mean probability theory or what? Okay, so it's important to be clear on those distinctions. There's another ambiguity too, which often leads to a shifting of the goalposts in the literature, because it depends on what you call the phenomenon. So let me give an example here, right? So you might ask yourself the question, let's take an entangled state. Oops. Is there a local hidden variable theory that reproduces the predictions you can get from that state? Now, if you're analyzing the EPR paradox, where you only measure the two systems in the same basis, you know, so you'll find that if you measure 0 versus 1, they're correlated. Obviously, there's local hidden variable theory for that. Just predetermine what those measurement outcomes are at the beginning, and you're done, right? So if I make the claim the EPR paradox is classical based on that, that would seem to be okay. But somebody else might come along and say, well, no, actually, if you measure them in different angles, you get Bell correlations and you violate Bell inequalities. So the EPR paradox is non-classical, right? Okay, this kind of argument happens a lot. It's not the EPR argument that's non-classical. It's the Bell argument. So, you know, if you say, oh, I've reproduced this phenomenon, and then somebody says, oh, no, but the phenomenon is actually something different, then obviously you can get into a situation where, you know, where the lines get blurred. So it's important when you do this kind of analysis to say exactly what distinction you're trying to draw and why it's an interesting one, and also to say exactly which features are definitive of the phenomenon. Okay, and these are one of the reasons. So there's a set of criteria which is really due to Rob Spekkens, which seems to be sort of a fairly robust and interesting notion to consider. So on the classical side here, really, like the strongest version of it is to say, you take classical mechanics. So Liouville mechanics is just classical mechanics where you're uncertain about the initial state of your system. So you're working with a probability distribution rather than a precise state. And you make what's called an epistemic restriction, which is to say, actually, only certain initial probability distributions are allowed. There's a limit on how well you can know things. And then you ask, okay, does this phenomena exist in this theory? That's a fairly robust notion of classical because, you know, Liouville mechanics is very classical. Now, there's a sort of slightly, shall we say, is it weaker set of weaker criterion, which is technically, and don't worry if you don't know what these terms mean, can be reproduced by a non-contextual local psi epistemic ontological model. So these are all properties which we would like to have of our theories underlying quantum mechanics, but there are no-go theorems for them. Now, it does seem that almost anything that is here, although there's no strict proof of that, okay? There's no strict proof that these are really equivalent. But generally speaking, when we look at these things, when we find a classical model, it tends to be of this type. So then the definition of non-classicality is that it requires a contextual model. Okay, so in the case of interference, specifically, so Rob has written a number of papers about this, which look at different quantum phenomena. Other people, including myself, have as well. But in the case of quantum interference specifically, these phenomena, we proved, at least, again, it depends how you define the phenomenon, but the kinds of features that are usually pointed to as being weird, mysterious in quantum mechanics, we can reproduce in these classical models. By the Einstein-Feynman paradoxes, I just mean the usual narrative about the double slit experiment, which is actually due to Einstein originally, although made famous by Feynman's lectures. So all of these things in the context of Mach-Zehnder interferometry, we have a model for, and I did discuss that model here at the interaction-free measurement workshop. So if you were there, you've seen that. So what I want to focus on today is these things that are to do with quantum interference, and however we show that you need to have non-classicality in this sense form. Okay, so is it clear where I'm going? Okay. All right, so by the way, for some reason, it's popular, people in this department, to show pictures of your papers in your book. I don't know why. But everyone else is doing it, so so this is the paper that has the model, the classical model for the basic interference phenomena. Okay, so in order to make progress here, I have to tell you what Spekkens noncontextuality is. There are many ways of developing this. I want to develop it in a kind of unified way so that you can see that all the different notions of non-contextuality that I'll be using are really the same thing. So I'm going to spend a little bit of time on this, and it may be, for those of you who are familiar with this already, it might be developed in a slightly different way. Okay, so we're going to start with the notion of an operational theory. So an operational theory is really a theory that allows you to make predictions when you specify what you're going to go and do in the lab. Okay, so the basic element here is an operation, or sometimes called a gate. Here it is, and it has three things. So it has input wires, output wires, and potentially a classical outcome. Strictly speaking, I can say it always has a classical outcome, because if I make it a singleton, then it's equivalent to not having an outcome. But so the wires have type labels on them. So you should think of these as type of system. So physically, what this kind of thing might represent is some physical device that's set up in a particular way. So for example, you think of it as a list of instructions. So maybe you have some optical device, such as a beam splitter. It has two input ports, right? So these wires would represent the input ports, and maybe immediately after the beam splitter, there's some kind of a detector. That detector produces a classical outcome, etc. So these gates correspond to that kind of thing. Okay, just an abstraction of that. So we can distinguish a few different types of operation. So if something has outputs but no inputs, we call that a preparation. It might have several outputs. If something has inputs but no outputs, we call it a destructive measurement. So it destroys the system in the process of measuring it. And generally speaking, if we have inputs, outputs, no classical outcome, we tend to call that a transformation. Okay, and those are really the types of operation that we're going to be using most often in our proofs. But in any case, so you can compose gates by connecting output wires to input wires if they're of the same type, right? So remember, this means system type. So photon traveling along an optical fiber, I need to connect it to something that can handle that same kind of system. So the system types represent that. And what I call a circuit is where if I compose a set of gates and there are no dangling wires at the end, right? So there's no input or outputs left. Then that circuit, I'm being a bit schematic here, but that circuit will be defined, strictly speaking, by a list of gates and a wiring. Okay, so the gates tell you what gates there are, and the wiring tells you which input and output wires are connected to each other. So given such a circuit, an operational theory must supply a rule that tells you what the probabilities for the classical outcomes are given any such circuit. Right? That's what an operational theory must do. Any questions about that so far? There are, of course, more constraints that we would typically put on these kind of theories, but we're mostly interested in quantum versions that are described by quantum mechanics. So if this theory is correctly described by quantum mechanics, then the system labels will correspond to different Hilbert spaces, potentially different Hilbert spaces for different systems. Yeah.
Yeah. So the previous slide, you care only about the joint probability, and you don't care about the conditional probabilities, or do they not matter?
Well, I mean, I can calculate the conditionals from the joint probability. I mean, this is just one way. I mean, in principle, everything's conditional on your choice of gates and wiring, right? So that's why there is something on the right of the conditional is the circuit, right? But yeah, I mean, you certainly could calculate other things and formulate things in different ways. But here, these classical outcomes are always outputs. I'm never considering them inputs to the operation. Obviously, you can do more sophisticated things. You can also do, like, in principle, this isn't adequate for everything because, you know, in quantum computation, for instance, you want to potentially make your gates depend on the classical outcomes in, say, measurement-based computing or something like that. So you may want to allow in this framework for gates to depend on outcomes and things like that. But we don't need to do that for our present purposes. Just try to do the simplest version of a framework that's unified enough to define what I need. Okay, so in quantum mechanics, a gate is represented, generally a gate is represented by what's called a quantum instrument. Okay, so this classical outcome variable is going to have some set of possible values, usually discrete. So little xg represents one of those values. So for each of those values, we have, and this is just the example for this gate, we have a map from the linear operators on the input wires to the linear operators on the output wires. So this is what that is in this case. That has to be a completely positive map because we know that we need to have a completely positive map to represent some kind of quantum dynamics. And if I sum over the different outcome values, then that's like, okay, you do this measurement and you forget the outcome. So that should be a valid quantum dynamics. And so that needs to be trace preserving. So it maps density operators to density operators.
Matt, I'm sorry, what is completely positive? What does it mean?
So if I take a positive operator and I act with a map on it, it's called a positive map. If it maps positive operators to positive operators. If I take my system and I tensor it with another system, and I consider a positive operator on the joint system, but apply my map only to one of the subsystems, right. If that gets mapped to a positive operator, it's called completely positive.
I see. Okay.
And those are different. Okay,
yeah,
it's not the same.
Thank you.
An example of a positive but not completely positive map is the transpose operation of a matrix.
Oh yeah, okay. Yeah, thank you.
Okay, so anyway, we're interested in, so the point is that this subsumes all the usual things that we use in quantum theory. So if you only have outputs, then this is a map from, you know, from nothing to a system, which is going to produce a density operator. So in this framework, the preparations will be represented by some density operator on the Hilbert space of the output wires. A destructive measurement will generally be represented by positive operator valued measure. So you need to get to the chapter of the Andrews book where
I'll get there soon.
So there's a set of positive operators that sum to the identity. They're the most general kind of measurement operators we can have. And if I have a transformation, then with no classical output, then this is just going to be a completely positive trace preserving map, or otherwise known as a quantum channel. Unitary dynamics is a special case of that, for instance. But they're all just examples of the same type of object. They're just specific examples of a quantum instrument. Okay, so in quantum mechanics gives us rules for computing the probabilities in this case. So this is just an example for this circuit. So these two gates at the bottom, the preparations, they represent density operators on different systems. Then we apply this dynamics and this dynamics tensored together. And then at the end, we have this PAVM. Actually, this box here with no output, this has, in quantum mechanics, this has to just represent a trace operation. So all that's happening is that we trace over system 5. So that's the Born rule probabilities. So if any such setup, quantum mechanics tells us how to compute the probabilities. Okay, so what we want to talk about, however, is reality, or at least proposed models of reality. So what we want to do is say, well, suppose our systems have some kind of real physical properties that objectively exist independently of us. So on each wire, there's going to be, each system type is going to have what we call ontic state space. I'm going to basically assume that everything is, all sets are finite here. In general, in the full version, you would use a measurable space because we just need to be able to define probabilities on them. So each wire type has an ontic state space, and on each wire there is some state. So I call these lambdas. Each wire has its lambda. And this can be any classical set. You know, they could be particles with definite properties, or it could be something abstract. You know, colors, whatever. You know, just some property. The lambdas are labels for those. So because these are, you know, we have to say, well, what does this dynamics? How is this? You know, how do these gates act on the on these ontic states, and how is that related to what we see? Well, these gates are going to be represented by stochastic transformations. By the way, I have a notational convention which you may have noticed. If something refers to an operational theory, I always call it prob. And if something refers to an ontic model, I use PR. That's just a simple distinction that so you can see what you're referring to. So basically, what happens here is that obviously the output, which is lambda 3, and the classical variable, depends some way on the input. And that can be probabilistic in general. So we have a stochastic transformation matrix. And, you know, as I said, I'm going to, for the purpose of this talk, just deal with a finite number of finite ontic state spaces. Okay, right. So again, in an ontological model, you can say, well, what are the special cases? So you have no, if you have no inputs and no classical outcome, then you'll just have a probability distribution. If you have a destructive measurement, we call these things response functions. So they basically tell you, given lambda, what's going to be the probability of getting the different outcomes. And the transformation itself is just going to be a stochastic map without any classical outcomes. So that's all straightforward. And then, you know, just analogous to what we did in quantum mechanics, we can calculate with this classical model. All you're going to do is take all of these stochastic transformations, multiply them together, sum over all the things that we don't observe. So we don't observe the lambdas, they're sort of hidden variables. So you sum over all those, and that will give you the probability distribution of the circuit. I probably should have conditioned this on C. So yeah, but anyway, so the point is that we have, of course, things that we represent according to quantum mechanics. So for those same experiments, we're going to say, oh, can we develop an ontological model of it? And if so, what kinds of properties does it have to have? Okay, so now I want to define Spekkens contextuality. So I'm going to introduce a class of things that I call testers. By the way, I mean, I haven't made this explicit, but it should be clear that composition, if I take gates and compose them by connecting wires, that in general creates another gate that is supposed to exist in the theory. So we assume that you can do compositions. So if I take any gate, and this could mean, you know, fragment of a circuit in general, then I can imagine an object which just completely closes it off, right? So every output wire is connected to an input wire, every input wire is connected to an output wire, and this thing produces some classical outcome like this. So there's a whole class of these things that exist in the theory. which are testers for this type of gate. How do you actually construct a tester? Well, all it really is it has to be a preparation, because we want no dangling wires at the end of the day. It basically has to be a preparation composed of the measurement, and the only slightly non-standard thing is that in principle they can be correlated by due to some other system, which this can be an arbitrary system label. Okay, so anything that looks like this is going to be a tester for the kind of gate that I had there. Okay, so special cases, measurements are going to be testers for preparations. Preparations, I mean, strictly speaking, it's preparations with a classical outcome are going to be testers for measurements. It turns out you don't really need this classical outcome here because, well, in quantum mechanics and in an ontological model, it has to be uncorrelated from the measurement by causality. All right. So we can now define a notion of operational equivalence. So we say that two gates are operationally equivalent. So we're defining this equivalence relation here between G and G prime. If, well, they have to have the same wires, the same wires with system labels, the same set of possible classical outcomes. And then if I attach them to the same tester, any tester, I choose any tester I like, and I attach both of them to that tester, then they should predict the same probabilities. Okay, so in that sense, what I mean by this is I have these two physical procedures for doing them in the lab. I do whatever I can do experimentally to investigate those. Right, so I attach them to other equipment in any possible way I can imagine, and I ask myself, can I ever distinguish the two? And if the answer is no, then we say they're operationally equivalent. Is that notion clear? Yeah.
So xg and xg prime, they're like the same output, or?
They, I'm calling them different variables because they are, this is the output of G prime, and this is the output of G. But as I said, they have the same set of possible outcomes. So this is really shorthand for, well, write it on the board. So I'm using sort of shorthand notation, like really I should write from xt is equal to little xt, xg is equal to little xg, tg equals to it's the same value on both sides. XT, XG. Right. So that's
And that should be a G prime.
yes, G prime. So that's what that means, but it's tedious to write that out all the time. So this is just shorthand for that idea.
Also, so the tester needs to be the same when doing this comparison, right?
Yeah, because if you put different testers even on the same gate, you'll get different outcomes. So we're trying to determine if we should at least operationally think of these gates as doing the same thing, right? And so if you test them in the same way and they react in the same way, then they're the same in that sense. Okay, does that make sense now? Okay.
I would just like to make a little remark, like in my area of programming languages,
Yeah.
we use kind of formalism that look very similar to this for similar reasons, right?
Yeah.
So
I mean, I could.
that's an interesting.
I can
remark,
certainly formulate all this stuff in category theory language and using.
This looks also like a bit like string diagrams.
Yeah,
right?
exactly. You can do all of that, but I'm trying to keep the formalism minimal.
No, it's fine. I just wanted to.
Right. So now we can define what it means to be non-contextual. So suppose we have an ontological model of some operational theory. So we have the operational theory supplies us our predictions, but we also have some underlying ontological model which we are trying to propose to reproduce the same physics. We say that the model is Spekkens non-contextual if whenever we have two operationally equivalent gates, they are actually the same at the ontological level. So that means that if we find two gates that we can't tell apart experimentally in whatsoever, then what they're doing to the underlying states of reality is actually the same. They're represented by the same stochastic transformation matrix. Now, this is usually, well, one way of arguing for this, there's a couple of ways of arguing for this, but one is just to invoke a Leibniz principle, right? So the identity of indiscernibles. So here we have two things that there's no experiment I can do to tell them apart. So the simplest explanation for that is that they're actually doing the same thing. It's not the only explanation. The other kind of argument that's given, and I've written papers on this, and so has Rob separately, is that there would be some kind of fine tuning, right? So it's possible that your theory doesn't give you enough testers to fully tell these things apart, and that could be why they look the same. But you'd have to sort of imagine that your testers are sort of fine-tuned in some way so that you can't find one that reveals certain kinds of properties. And that would seem to be a little bit conspiratorial. So we want to look at theories which rule that out.
So when you say fine-tuning, is that a technical notion?
Yeah, there's technical literature on fine-tuning. Causal fine-tuning certainly, but Spekkens and I separately, we've proposed different, slightly different formalisms and notions for fine-tuning. I obviously prefer my one. I have a paper with Lorenzo Catani that was also published last year about this notion of fine-tuning.
And can you say again what fine-tuning means in the context of this formalism?
So imagine that these two were actually different stochastic matrices. It's possible. So if we allowed if our testers were any process in principle allowed by the ontological theory, imagine those preparations and measurements were any possible stochastic transformations that are allowed, then we would be able to tell them apart because you can tell different transitions apart. But maybe in our operational theory, there's going to be some restriction on what testers there are. Nonetheless, you might have thought that it's likely that you're going to have enough testers to be able to see when things are really different. Otherwise, there's some restriction on your testers, then they're not giving you full information about your gates. And you have to ask yourself, why? Well, there's some fine tuning in the parameters specifying your testers, is the idea. We can go into that more.
So fine tuning restricts what can be tested?
Fine tuning is restricting what properties of reality, if we think of it like that, can be determined by testing in this way. Okay. This is taking longer than I imagined, but the point is to just, by the way, that there is a reason for being interested in this, which has to do with quantum information, which is just that if these two things are equivalent in quantum mechanics, there won't be any way of telling them apart. If I'm trying to do a classical simulation of that, it will basically be an ontological model. And if we can prove that it has to be contextual, then this tells you that any classical simulation of this process has to make additional information available beyond what quantum does. And we can typically exploit such effects for things like cryptography, right? So this is applications of contextuality have come up in those areas. That's another reason for being interested. Okay, so what are the consequences in quantum theory? Well, if we have a quantum mechanical model, we know that two preparations are indistinguishable if they correspond to the same density operator. So this probability distribution in a non-contextual model now can't depend on, it doesn't depend on the preparation in any way beyond what density operator it prepares. Similarly, the response functions can only depend on the POVM elements. The stochastic maps can only depend on the CPT maps because those would be our operational equivalent in quantum theory. So I can, by the way, if I apply non-contextuality to this, I will call it preparation non-contextuality, measurement non-contextuality, transformation non-contextuality, but they're really examples of the same thing. So one thing we can say is that suppose in quantum theory there exist sets of states, like two sets of states here, and probability distributions such that when I make a convex combination of these two, they give me the same density operator. Well, those correspond to preparations, right? So I can roll a dice with these probabilities and then prepare one of these states as a result. Similarly over here, those correspond to two operationally equivalent preparations. And so because of that, these have to correspond to the same probability distribution. So in the ontological model, non-contextual, you'd have to have the convex combination of these probability densities would be the same as for this one. Okay. Okay, so that's basically what I need. So mostly, for the short amount of this talk that remains, mostly I'm going to use preparation non-contextuality and transformation non-contextuality. Those are the two that work here. So let's talk about now the uncertainty relations for a qubit. Mainly the reason why we discussed this was because of its relation to interferometry, but it turns out that you can just sort of abstract out this piece. So here's a picture of the paper because we like to put pictures of papers. Okay. So consider a qubit, and we have the Pauli observables X, Y, and Z. If we consider two of those observables, say X and Z, then the strongest uncertainty relation, I mean, I can qualify this if you like, that you can make between those two is this. So, by the way, I'm assuming here that eigenvalues of the Pauli observables are plus and minus 1, not plus and minus h bar 2 or whatever. But, so that's the way that things are normalized, okay? So for any state, these are the standard deviations that you get. Now, you can show, and we do this in the paper, I'm not going to go through the whole proof, that because these measurements happen to have outcomes plus or minus 1, this relation here is necessarily equivalent to this, okay? Now, you can think of the magnitude of the expectation value as quantifying your degree of certainty, right? Because if it's 1 or minus 1, then you know exactly that the probability of 1 or minus 1 is 1. And so the closer this is to 1, the more predictable the outcome is. So you can think of this relation here, if you think of this as an uncertainty relation, you can think of this as a certainty relation. There's a trade-off between certainties. But for this kind of observable, it's equivalent, and it's going to be easier to work with those expectation values. Okay, so we can consider, so again, I don't want to go into a huge amount of detail, but there's a whole framework for alternative theories, potential theoristic quantum mechanics, where the idea is that in quantum mechanics, you have your set of density operators as a convex set, and we can think about probabilistic theories where this convex set is replaced by other sets, right? And they have names, and they have, you can develop the theory of them. So in these theories, you're going to have different trade-off relations, right? So this is the theory that comes from what's called the stabilizer states in quantum mechanics. So note that it doesn't have the squares here. One thing we can do is consider, suppose you can't prepare pure states in quantum theory, but everything is immediately depolarized by a certain amount, and that will modify this trade-off here. And then this is what's called the G-bit theory. It's, for those of you who know about PR boxes, it's like 1/2 of a PR box. And a simplicial theory here, if the state space is a simplex, then the theory is basically just classical probability theory. So this one's talking about classical probability theory. There's really no constraint in either of those two theories on the expectation values.
So don't the conditions on D and E look the same?
Sorry?
Conditions
Yes,
for
they do. For this particular thing. I mean, they're different theories, but we'll see that one of them is contextual and one of them isn't, because there's an additional condition that's missing on the simplicial theory, and this is one of the reasons why I'm introducing. Now, so in order to prove contextuality, preparation contextuality, we're going to need some operational equivalences. No operational equivalences, and there are no constraints. And so these, I don't have any, like just saying this is the uncertainty relation doesn't tell me what states I have. So I need to impose an assumption on states. Right, so in particular, the simplest case in which you can prove any kind of contextuality would be if you have 4 states, because then I can take 2 different convex combinations and find that there'll be an operational equivalence here. So we need something like that in order to get going. So the way we do that is that we assume if we have some state in our theory, rho 1, and this could be a quantum state or one of those GPT states, there have to be 3 other states such that the expectation values are the same magnitude, but we have all possible signs, all possible sets of signs. So for rho 2, the x expectation value is negated and the z one is the same. For rho 3, they're both negated, and for rho 4, only z is negated. And then we also want these 4 states to satisfy this operational equivalence. Okay, so when I make a convex mixture of rho 1 and rho 3, rho 2 and rho 4, I get the same state. Okay, so we call this A21 orbit symmetry. That's the Kirkster group, because what we're basically doing is reflections of a rectangle. And this is the symmetry group of reflections of a rectangle. So to be a bit more concrete, this is how it looks for a qubit. So if I take any state S1, this could be inside the Bloch sphere. You can basically, if you put a plane, if you put a plane that's parallel to one of the planes, XZ in this case, through the Bloch sphere, you can find the other 3 states that have this symmetry. They're basically just going to form a square in this case, and that's basically how you do it in quantum theory. Now, all of the examples of theories that I gave satisfy this, except this one, right? So, if I choose one of the vertices here, then there aren't enough symmetry transformations to generate all 4 states that I need. Okay, so although these have the same uncertainty relation, the difference is that the G bit obeys the A21 orbit symmetry. Okay, so I'm just going to, right, so the proof of this is in our paper, and due to lack of time and the relative straightforwardness of the proof, in the sense that it just employs fairly standard algorithms, you can show that any non-contextual theory that satisfies this orbit realizability condition must have this trade-off relation. I'm sure I put the diagrams in here. But anyway, what this shows you is that, let me draw the diagram. So if we have the predictability of x and the predictability of z, like this, in quantum theory, we're going to have something like this. And then for a non-contextual theory, it has to be like this. So we can analyze all those other theories as well. If you look at the depolarized theory, then there'll be some amount of depolarization where the curve touches here, and that amount can be accounted for in a non-contextual theory. So if you have that amount of depolarization, I think it's about 2/3. Anyway, I did put the graph on these slides, but it seems to have disappeared. And then for the G bit, you see you get this, and that also violates the bound. So yeah, that's basically the idea. And any questions about that before I move on? Okay, so I want to go to the Oh, yeah, no, I need to talk about this as well. So what does this have to do with interferometry, which is where I started? We've gone a long way from interferometry. The point is, oh yeah, there's a picture of the paper. It was an editor's suggestion. Look, it shows us that we could have got it in a better journal. I want to consider this Mach-Zehnder interferometer setup. So I basically taken the interferometer and divided it into two pieces, because this bit down here I'm going to consider to be my preparation. So I have a laser which goes into a beam splitter. This can have an arbitrary reflectivity in general, and it can have an arbitrary phase shift here so that we can prepare essentially any qubit pure state. So you have the two arms of the interferometer. This is the preparation. Then we have a choice of two measurements. We can just straightforwardly go ahead and measure which path the system is on, or we can recombine the beams on another beam splitter and do the usual Mach-Zehnder interferometer measurement. Now, in this context, in quantum mechanics, it was proved, like, so there are various relations which are called wave-particle duality relations of different types. The type I'm considering here was for the double slit experiment originally derived by Wouters and Zurek, but Greenberger-Yasin did the version for the Mach-Zehnder interferometer, showing that the fringe visibility squared plus the path distinguishability squared is less than or equal to 1. Now, this type of relation is really just an uncertainty relation, because let's look at the definition. So the path distinguishability is, we take this first measurement here and we look at the difference between the probabilities, absolute difference between the probabilities. So if you identify your left and right states with 0 and 1 of a qubit, then this really just is the magnitude of the expectation value of z, as we had before. The other one is the sort of a which phase measurement, but this beam splitter, what this beam splitter does is it swaps x and z. So the which phase measurement is basically a measurement of x, but then you have to deal with the sort of slightly more murky definition of fringe visibility. But in the case where you only have two possibilities, the sum, so unlike in sort of the double slit experiment, where you have a denominator, non-trivial denominator, in this case, the denominator will be 1, because the probabilities must sum to 1. And then the fringe visibility just says, take the maximum intensity minus the minimum intensity, which in quantum mechanics is the probability. And so that also turns into just the expectation value of x. And so the wave-particle duality relation is really just the same as the qubit uncertainty relation. So everything I've said about the qubit uncertainty relation follows here. Okay, this time I did manage to include the graph. So in a non-contextual theory, we would have to have the visibility plus the path distinguishability be less than or equal to 1 rather than their squares. And so you would get this graph. Notice that in the extreme cases, these graphs meet. So this corresponds to cases where the original beam splitter is 50-50 and the phase shifter is either 0 or pi. Okay, and then we can either measure which path we're on, or we do the interference measurement. That is the full set of things that people consider in a lot of these paradoxes, like the Elitzur-Vaidman bomb, the Feynman paradoxes, and so forth. And we have a non-contextual model for that, and this analysis shows, this analysis also agrees with that. These are the points at which you could potentially have a non-contextual model. So you really have to go beyond the sort of the 50-50 beam splitters case to find something that we would want to call genuinely non-classical. Okay, I'm really running out of time. So I was going to present the proof of this because it's you, but I think I'm not going to present the proof. I'll just tell you what it is. And then you can ask me later if you wish. So the quantum Zeno effect. So consider a qubit that's initially in the state 0, and it evolves under this Hamiltonian. Alpha is here a constant. So after a time t, and I'm assuming h bar is 1, the system evolves to this. If I take time pi over alpha, then the system will have evolved into an orthogonal state. Okay. Now, suppose I break up this time interval into short intervals, n could be some large number. So break it up into short time intervals. And after each such time interval, I'm going to measure in the 0, 1 basis. If I get the outcome 0, I'll continue with the experiment. If I get the outcome 1, I'll abort. So after the first time step, I will have this state, and the probability of continuing is going to be this. If I continue, the state will collapse to 0. So after the next time step, I'll again have this. So getting through the probability of getting through all 10 time steps is this to the power n. And then you look at what happens. Okay, you look at what happens for large n. You can see from this that the probability of continuing for n steps, for all n steps, goes to 1 as n goes to infinity. Each time I continue, the measurement resets the state to 0. So here's what I can conclude will happen. If I'm not making measurements at all, then the state will evolve to something orthogonal. But if I repeatedly make measurements at a rapid rate, then the state will be frozen to 0. And this freezing to 0 is what's called the quantum Zeno effect. Okay. So for a non-contextual model of the quantum Zeno effect, so we require that it does evolve from 0 to 1 in the correct time when no measurements are made. You can show that the probability of failure at each time step must be greater than or equal to 1 over n. Now, for this proof, I used both preparation non-contextuality and transformation non-contextuality. It's sometimes the case that you find when you use transformation non-contextuality, you could instead have used preparation non-contextuality, but I haven't figured that out. But anyway, the proof is more easy when you consider transformation non-contextuality. So consequently, in the non-classical, in the non-contextual case, this is going to be the probability of passing all steps. And if you take the limit of that as n tends to infinity, you get 1 over e, which is much smaller than 1. So it turns out that you can't freeze with unit probability even in the limit if you're non-contextual. Now, this has applications for what's called the Zeno-based interaction-free measurement. So this is a wrinkle on the Elitzur-Vaidman bomb. So what we're trying to do is take the Elitzur-Vaidman bomb and make the probability that the bomb explodes go to 0, whilst at the same time the probability of detecting it if it's there correctly go to 1. So what you do is instead of having 50-50 beam splitters, you have a beam splitter where it's overwhelmingly more likely to be reflected up here, tiny probability of going down there, and the bomb fuse intersects the path each time you go through the interferometer. So the beam splitter is actually implementing this transformation, which is the one that we were considering, and the bomb is acting as a measurement. So basically this does the Zeno effect. So if there's no bomb there, then this goes to something orthogonal, and the system comes out of the photon comes out on this path. If there is a bomb there, then the probability of continuing, the probability of continuing goes to 1, and the state stays as it was at the beginning, so it will come out there and you detect the bomb. That's basically the idea. But since we know you can't do this with a non-contextual model, we can compare what happens. So if we look at the number of time steps, how the quantum model, the probability of detecting a bomb without it exploding goes to 1, this one goes to 1 over e, okay? And then we can look at the probability of a false negative. So this tells you there's no bomb when there's really a bomb there. Fortunately, both of those tend to 0, but the non-contextual model has to do it a lot slower. And then this is probably the worst one. The probability of the bomb exploding, if it's there, it goes down quantum mechanically. In the non-contextual model, it actually goes up. So it's worse than the just single step version. So this is actually pretty bad. This tells you that there's something highly non-classical about the quantum Zeno effect and this. I do want to say that prior to this work, there was another connection. I'm not going to go into details. There was another connection between interaction-free measurement and contextuality was derived by a different group, but it's a different setup. Okay, so see, I had to make. So I can present the proof of that if you want, but I know I've gone on for long enough. Okay, so what I want to say is that if you're going to have arguments about what is classical or non-classical, we should be trying to back that up by rigorous no-go theorem. Do you want to claim something's non-classical? What notion? What's the theorem that shows that it violates that? So these aspects of quantum interference, they've traditionally been regarded as mysterious, but they all turn out to be classical on the Spekkens classification. However, there are these more subtle aspects that require us to consider quantum contextuality. So some possible future work. If you really wanted to experimentally test the Zeno IFM thing, then you can't assume there'll be no false positives. So you have to see what happens with false positives. And that's also related to this idea. So, you know, there have been tests of these trade-off relationships that people have done in the lab. But in order to really check if they're non-contextual, there's more measurements that you have to do. So one could try and do a robust demonstration of non-classicality based on quantum interference. And we have to think about the setups for doing that. Okay, so I'm going to leave it there. Thank you very much.
Thank you.
Sure. Emily, yeah.
Yeah, thank you. This is really cool. So I've always thought of the quantum Zeno effect as being related somehow to the continuity of transformations in quantum mechanics, which of course is what Hardy sees in the five reasonable axioms is the difference between quantum mechanics and classical mechanics. So I wonder, is there a way to understand the connection between those two notions of classicality in the context of the Zeno effect?
I mean, I'm not sure that I agree that it fundamentally has to do with continuity, right? So, I mean, you can imagine an analog of the Zeno effect classically with a bit, where you have some transition where it's there's a small probability of transitioning from 0 to 1 in any time step. If you're at 1, you stay there.
Yeah.
And then, so after as n tends to infinity, you'll go from 0 to 1. But if you keep measuring and Bayesian updating, then you will overwhelmingly, with high probability, update to 0. Now, so that's analogous, and it's you know, stochastic transformations rather than. Why isn't it perfectly analogous? Because this is one of the features I emphasized. You go from 0 to 1 in the quantum Zeno effect in a finite amount of time.
Yeah.
You can't do it by a stochastic model classically without that effect. So it's not, you know, just that you can change things a small amount in each time step. It's that compounding those gets you somewhere orthogonal. And this is sort of, if you impose that this happens in a non-contextual model, that's what tells you, oh, well, you know, the system has to move sort of further in each time step than it does in quantum mechanics.
Oh, okay.
Yeah.
I think that makes sense.
I mean, I can show you the proof if you want. It's not that
I'd like to
hard.
see the proof of that.
It's a little bit involved, but it's not that difficult. Other questions? Okay. Oh wait, look, I'll just check if there's anything online. I don't think so. Okay.
Maybe I can ask you a question. It's not a technical question. So, are there any models, ontological models, which are non-contextual for exactly these scenarios, which are not problematic according to the solution?
Yeah.
And they become contextual.
Oh, they become contextual. Okay, so you know what we have is basically a version of the Spekkens toy theory of loops, and it can't be extended.
Like, cannot be.
It can't be extended. Obviously, it can't be extended with the matter of making it contextual because that's what we proved here. So we have that model, and it's very nice for those cases. Yeah, but it obviously can't be extended. Now, if you have something in mind, like you know, I give you quantum mechanics and you come up with an ontological model that reproduces all of quantum mechanics, and then you look at these specific phenomena and you find in those cases the model that happens to be non-contextual. I don't know of anything like that. As you know, we tried to come up with something like that based on the Wigner function, because it does turn out that you have positivity in the Wigner function in all of these cases that are the non-problematic ones. So possibly something like that may still work out, but you know, we didn't get it to work out.
So on the one hand, you have like this Spekkens kind of models, which can give a non-contextual explanation for this, but they cannot explain this wave particle to the trade zone. On the other hand, you have these other kinds of models, which probably are contextual in these, according to you, like non-problematic scenarios as well.
Yeah. So the Broadband theory, for instance, would be an example of that. So it's you know, I would say it's more contextual than it needs to be. I mean, it needs to be contextual because we have these no-go theorems, but it also is contextual and local in situations where we can't prove that. I mean, I sort of believe in and people have, you know, Harvey Brown criticized me for this. So maybe it's wrong, but I kind of believe in a principle of trying to minimize wins. If we have some phenomena that does have a reasonable classical explanation, then I believe things would be better if that were the explanation. Certainly, if we want our interpretations of quantum theory to be useful for things like helping us determine which phenomena are likely to have quantum advantages, then if we have an interpretation which doesn't have quantum weirdness where it isn't needed, that'll be more useful for that. So if you think that the correctness of interpretation is in any way related to how useful it is in some way, if you're pragmatic to that extent, then I think, you know, this principle of trying to minimize weirdness makes sense.
It's a bit subjective.
It's a bit subjective, but you know, I mean, obviously, you know, at the beginning, I went through this idea of, you know, what does it mean classical? So you might have different criteria for what you think are classical, but basically you might want to say that if something has a classical explanation in whatever precise sense I've written down, then I want that to be the explanation in my interpretation of quantum mechanics.
Okay.
So in this case, I would say something like, well, if Liouville, epistemically restricted Liouville mechanics precisely recaptures this phenomenon, I would like that to be, you know, basically the theory that my interpretation supplies for that case.
What
Is
if
it
I
possible?
were like, I think epistemic restrictions are weird?
Sorry?
What if I were like, I think epistemic restrictions are more weird than contextuality?
Well, okay, then I would have an argument with you. I think they're weird as fundamental principles. I'd agree with you about that. But I do want to bear in mind that the kinds that appear in Spekkens toy theory are of the sort where if you impose at the beginning of time that you have this particular probability distribution that satisfies this restriction, then it will continue to hold for all time. So it's not weird in the sense that we're sort of continually projecting some fact about our knowledge on reality. It's just, you know, if for whatever reason there's a restriction on what the initial condition was, such that the best you can say is that it's this probability distribution, which is kind of what we expect the initial conditions of what we know about the initial conditions of the universe to be like, then that's what we'll see. And if that isn't the case, you may also imagine that perhaps there's some kind of equilibration process that drives things into that state as well. So that's also, you know, a possible kind of explanation. So when I say epistemic restriction, I'm not really imagining that that's a fundamental physical principle. I'm imagining it arises from some facts about the initial conditions of dynamics. Anything else? Not. Thanks again.